Today, we're going to be walking through one of LeetCode's most popular problems, twosome. Let's get right into it. Given an array of integers nums and an integer target, return indices of the two numbers such that they add up to target. You may assume that each input would have exactly one solution, and you may not use the same element twice. You can return the answer in any order. Let's take a look at an example. We have an array of 3 elements and a target of 6. In this case, since adding the elements 2 and 4 gives us a sum of 6, we would return their respective indices 1 and 2 in a list. Note that although adding 3 and 3 also gives us a sum of 6, we couldn't have returned a list of indices containing 0 and 0 since we may not use the same element twice. In its simplest form, this problem necessitates us to add each value in the array with every other value in the array until we find a pair that sums up to the target. We can do this in code with a nested for loop. We'll iterate through the first for loop with variable I and through the second loop with variable j. Note that the second loop here starts at I plus 1 to ensure we don't use the same element twice. Since it's guaranteed that the list contains a pair that sums up to our target, we simply return the necessary indices once we find the correct pair of numbers. Let's take a look at these loops in action. When I equals 0, we're at the first element of the list, which is 2. When j equals 1, we're at the second element of the list, which is 9. Since 2 plus 9 equals 11, and 11 doesn't equal our target of 17, we continue through our loops. Let's fast forward these iterations until we find our intended indices. Here, we see when I equals 1 and corresponds to the element 9, and when j equals 7 and corresponds to the element 8, the sum of the elements 9 and 8 gives us 17, which is our target. As a result, we return the values 1 and 7 in a list. In the worst case, since our code would iterate through our list of n elements n times, we iterate with an upper bound of n multiplied by n times, which gives us a time complexity of big O of n squared. Since we're not storing anything extra in this approach, the space complexity is big O of 1. Can we do anything to improve our time complexity? It turns out we can. In our brute force solution, we compare each element of the array with every other element of the array using 2 pointers. What if, instead, we had a copy of our array stored in a hash map, mapping from the element in the array to its index, so that any value could be accessed in big O of 1 time? This map could quickly be created via a single pass of the array. In this case, instead of iterating through the array with 2 pointers to compare the sum of each pair of values, we could instead just reference this map whenever we need to find the complementary element for a value in the array. For instance, for the first element, we would see that the target minus the first element, or 17 minus 2, gives us 15, which means in order to return the element at the 0th index, we would need a complementary 15 in our list. Since this element does not exist in our map, we would move on. On the second element, however, we would see that the complement exists in our map since the target, 17, minus the element, 9, would give us 8, which exists at index 7. As a result, we would be able to return this pair. Since this approach would involve 2 independent passes over the array, the time complexity would be big O of n, a big improvement over our big O over n squared solution. Since we would be storing our n elements in the hash map, the space complexity would be big O of n as well. To bring this 2-pass solution down to a 1-pass solution, we can make yet another optimization, which is to build the hash map as we iterate through the array, instead of creating it beforehand. The idea here is that if the complement of any element has already been visited, we can reference that complement and return the pair during a 1-pass iteration of our array. If the complement is not in our map, however, we move on and continue comparisons until we find the pair. Let's take a look at how this would work. In our example, we start at the first element and check if the difference between the target and the element exists in our map. Since the difference between the target, 17, and the element, 2, is 15, and 15 does not exist in our map, we add the element along with its index to our map and move on. On the second element, we do the same. We check if 17 minus 9, or 8, exists in our hash map. Since it does not, we add the value 9 to our map with its respective index. This way, when we finally get to 8 in the 7th index, we subtract 8 from the target to get 9, and since this value was already visited at index 1 and exists in our map, we would simply return it in a list containing the indices 7 and 1 as a result. Although this approach provides an optimization, it still involves one pass over our array of n elements, so our time complexity would still be big O of n. Since we still allocate space for a hash map of n elements, our space complexity also remains at big O of n. Here is the final code for the one-pass solution. Thank you for watching.